Hi everyone, this is the presentation of my doctoral thesis, which is titled Robust Speech Recognition on Intelligent Mobile Devices with Dual Microphone. This presentation has been divided into two main parts. The first one is intended to present the introduction, motivation and objectives of this work, and the second part is intended to describe our contributions, experimental results and conclusions. So let's begin with part 1. Automatic speech recognition is a major technology under controlled conditions. And what do I mean with controlled conditions? Well, I mean fixed environmental or working conditions over time of the speech recognition system that are known in advance. So, for example, let us suppose that we have a speech recognition system intended to operate in a car interior. We can optimize this system in the knowledge that it's going to operate always in the same place. We're going to have the same type of noise over time. It's going to be used by the same speaker, I mean the driver, etc. So the point is that we can train this system in the same conditions that are expected to be found when being used in order to perform as well as possible. However, the problem comes when there's mismatch between training and testing data that can degrade the performance of the speech recognition system. Some mismatch sources are inter-speaker and inter-speaker variabilities, transmission channel reverberation, and one of the most important is background noise, which can make speech recognition systems unusable. Tackling background noise is one of the main scopes of this thesis. A speech recognition system is comprised of two main stages, front-end and back-end. The goal of the front-end is speech feature extraction, so for example male frequency capture coefficients. And the goal of the back-end is to find the most likely sequence of words from the set of speech features. So, returning to the noise mismatch problem, let us suppose that we have a speech recognition system intended to operate in a noisy environment, and to train this system only clean speech data were available. So because acoustic models are trained with clean speech data and we try to recognize noisy speech data, the most likely thing is that mismatch causes a wrong transcription. So how to solve this problem? First, we should model what's happening, and in this thesis we consider the classical linear speech distortion model, which has this form in the time domain. I mean, the noisy speech signal equals the clean speech signal convolved by the channel noise plus the background noise. And this speech distortion model can be alternatively expressed this way in other domains. So, from this mathematical modeling, we can take a look at how the statistical distribution of the speech energy is affected in the presence of ambient noise, in order to understand why the noise mismatch problem in our example. So, for the sake of simplicity, let's assume that there's no channel noise, and let us also assume that for every filter bank channel, both the noise and clean speech energies can be modeled by means of Gaussian distributions. So, as we can see from these graphs, as the noise energy increases, the speech Gaussian distribution is right skewed. If noise energy tends to be comparable to or greater than clean speech energy, the statistical distribution of a noisy speech tends to be similar to that of a noise. In other words, speech is masked by noise. A variety of algorithms can be found in the literature trying to mitigate the effects of the speech distortions, and the possible taxonomy of the noise robust methods for speech recognition is the one in this slide. So, for example, we have feature space approaches, and they work at the front-end stage. We have model-based approaches. They work by modifying the acoustic model parameters, and they are often more accurate than the feature space approaches at the expense of a high computational complexity. We have compensation with explicit distortion modeling, for example VTS applied for either model adaptation or feature compensation, And the missing data approaches handle uncertainty on the feature space. And of course we have many more approaches, for example stereo data learning based techniques, exemplar based techniques, etc. What's the motivation to carry out this research? Well, automatic speech recognition has experienced a new upswing thanks to the latest mobile devices, for example smartphones or tablets. And mobile devices can be used anywhere, at any time, usually in noisy conditions, so it's very important to tackle background noise in order to ensure a good performance of the speech recognition based applications. To do this, we can take advantage of the small microphone arrays embedded in the latest mobile devices. The third and fourth chime speech separation and recognition challenges are good examples to know what's being developed for multi-microphone robust speech recognition on mobile devices. And in particular, these challenges consider the use of a tablet with 6 microphones in everyday noise environments. And as we checked, performance benefits from a combination of single and multi-channel techniques. And in particular, spatial filtering is a popular choice for speech enhancement in this context. In these challenges, as we checked, beamforming shortcomings, like for example low directivity at low frequencies, are partially overcome by means of post-filtering. However, beamforming shortcomings are especially harmful in the case of arrays comprised of a few sensors close each other. For example, let's think about a dual microphone smartphone. And in this scenario, beamforming can even degrade the performance of the speech recognition system, so we're required to design specific solutions. So in the case of a mobile device with only 2 microphones, we have a primary microphone located at the bottom of the device, the main purpose of which is to capture the voice of the speaker, and we have a secondary microphone at the top or at the rear of the device, the main purpose of which is to get information about the acoustic environment. So this secondary microphone is placed in an acoustic shadow with respect to the speaker, and as a consequence, and as we can see from these graphs, speech is much attenuated at the secondary microphone with respect to the primary one. Moreover, diffuse noise fields are typically found in real-life environments, and as we can see from these graphs, similar noise power spectral densities are observed by both microphones, and this is valid for both close talk and far talk conditions. With close talk conditions, I mean that the loudspeaker of the smartphone is placed at the ear of the user, and with far talk conditions, I mean that the user holds the device in one hand at a certain distance from her or his face. So we can exploit these power level differences between the 2 channels of the device to design nice algorithms for robust speech recognition in this context. And what are the objectives of this thesis? Well, as latest mobile devices embed small microphone arrays, and the performance of beamforming for robust speech recognition on mobile devices is quite limited, our objectives are: first, reviewing the latest on single and multi-channel noise robust speech recognition for mobile devices; second, to develop a new series of algorithms exploiting a secondary sensor to improve the speech recognition accuracy on mobile devices; third, to generate new speech resources under dual-channel mobile device framework for experimental purposes; and fourth, to evaluate and compare our developments to draw conclusions in order to make further progress. And with this, I've concluded the first part of this presentation, and now I'm going to talk on the second part, intended to explain our technical contributions along with our experimental results and conclusions. So let's continue with part 2. In this slide, we can see a summary of the second part of the presentation, where our techniques, all of them working at the front-end stage, have been arranged into 3 different categories: multi-channel power spectrum enhancement, dual-channel vector Taylor series feature compensation, and dual-channel deep learning techniques. Most of the work done on multi-channel power spectrum enhancement has been gathered in two different papers. The first one was submitted to the Digital Signal Processing Journal, and the second was published at the 22nd European Signal Processing Conference. Moreover, this paper received a Best Student Paper award. As I've introduced, our dual-channel techniques are intended to exploit a secondary microphone. However, a mobile device can easily integrate several front sensors that can be exploited to provide further speech recognition robustness. So, in the case of a mobile device with several front sensors, we may apply beamforming to generate a virtual primary channel to be used by our techniques along with the secondary channel. As an advantage, we can highlight that this virtual primary channel has a higher signal-to-noise ratio than any other signal from the mobile device, thereby increasing the recognition accuracy. This way, our contributions behave as dual-channel post-filters. Our first technique is dual-channel spectral subtraction, which extends spectral subtraction to a dual-channel framework. So first, we consider our dual-channel speech distortion model in the power spectral domain, and we neglect the channel noise. At this respect, I should mention that during our experimental evaluation, we will generally apply capsular mean normalization for channel compensation. So the first equation corresponds to the primary microphone of a device, and the second equation corresponds to the secondary microphone. Then we establish a couple of relations. The first one relates the clean speech power spectra captured by both microphones through the speech gain term a sub to 1. This term might be estimated from a steering vector computation method for beamforming. However, as we will see later, we have developed a minimum mean square error based estimator to compute this parameter. The second equation similarly relates the noise power spectra at both microphones through the term G sub 1, 2, and this one might be estimated online, for example, from a minimum mean square error approach, which results in this ratio of noise cross-correlation coefficients. So by taking into account all of these relations, we are able to define this dual-channel spectral subtraction estimator of the clean speech power spectrum at the primary channel. And why at the primary channel? Because I remind that it is expected that the primary signal is less affected by noise than the secondary one. Our second technique is power minimum variance distortionless response, and this one is based on NVIDIA beamforming, but this discards the phase information to overcome the limitations of the classical NVIDIA beamforming when applied to the considered dual-channel framework. So we can compute the clean speech power spectrum at the primary channel from a linear combination of the dual-channel noise observation, where the optimal weighting vector can be computed by minimizing the mean square noise-dependent term subject to this distortionless constraint for the clean speech signal. So the final weighting vector has the same form as that from NVIDIA beamforming, where Fizeban is a noise spatial covariance matrix, and this vector plays a similar role to a steering vector referred to the primary channel. Our third technique is dual-channel spectral weighting, and this one is based on Wiener filtering. We began by considering two initial assumptions. The first one is that the secondary microphone captures no speech. In other words, that the clean speech power spectral density at the secondary channel is 0. The second assumption is the existence of a homogeneous noise field. And this assumption is reasonable as noise homogeneity is one of the properties of diffuse noise fields. And as I said, diffuse noise fields are typically found in real-life environments. So as a consequence, we have that we can observe similar noise power spectral densities at both microphones. So under these assumptions, we have that the noise power spectral density at the primary channel equals the noise speech power spectral density at the secondary channel. So Wiener filter can be easily estimated by just using the noise speech power spectral densities from the dual channel noisy observation. And well, these assumptions can be acceptable in some specific situations. For example, when we use a dual microphone smartphone in closed talk conditions, in general they will not be accurate, because the secondary microphone also captures a speech component, mainly by diffraction at the borders of the device, reflections from the environment, etc. So this implies that the speech gain term is up to 1 is non-zero, something that we can see from these histograms of a natural logarithm of the speech gain term is up to 1, obtained by means of a dual microphone smartphone used both in close talk and far talk conditions. And while the magnitude of this term is relatively small in close talk conditions, this is not exactly the case for far talk conditions. So we introduce a bias correction term to rectify the initial underestimation of the previously estimated Wiener filter. And we can, it is easy to show that this bias correction term depends on the speech gain term is up to 1. So far we have assumed that both microphones observe similar noise power spectral densities. However, the noise homogeneity property can be altered by different external factors. So for example, if we compute a virtual primary channel, or if we have different microphones with different characteristics. So we designed a noise equalization procedure to force the homogeneity assumption to be true. This noise equalization procedure transforms the secondary signal in order to follow the noise components from the primary channel, where beta is an overestimation factor inspired by over subtraction typically applied in spectral subtraction, which helps to reduce the musical artifacts. So, inspired by NVIDIA beamforming, we generate a new secondary signal from a linear combination of the dual channel noisy observation, where in this case the optimal weighting vector is computed by minimizing the mean square error between the dual channel noise and the noise component from the primary channel, subject again to a distortionless constraint for the clean speech signal. As we can see in this noise power graph, the equalized noise is much more similar to the noise component from the secondary channel, to the noise component from the primary channel than that from the secondary channel. In this slide, we can see a block diagram of the full dual channel spectral weighting system. So first, we require to estimate the speech gain term, as we will see immediately after. Once done, we apply our noise equalization procedure to force the homogeneity assumption to be true, and then we compute the power spectral densities of noisy speech signals to estimate the a priori signal-to-noise ratio to compute our Wiener filter. Finally, a post-processing stage is applied, which exploits the spectrotemporal correlation of the speech signal to refine the Wiener filter weights by application of a couple of two-dimensional filters. In order to apply all the techniques presented so far, we require knowledge on the speech gain term is up to 1. So here we propose a minimum mean square error based relative speech gain estimator, and this is performed in the STFT domain. So we define this speech gain vector, which in turn can be decomposed into its real and imaginary parts. So the minimum mean square error estimate of this speech gain can be expressed this way, where we have assumed statistical independence between its real and imaginary parts. I should say that a similar assumption has been previously adopted in the later TAF for the sake of simplicity. So now we can estimate the real and imaginary parts of the speech gain independently. So to do this, first we assume that the real and imaginary parts of both the speech gain term and the noise observation at the secondary channel can be modeled by means of Gaussian distributions, something reasonable as we can see from these histograms. Next, for the sake of simplicity, we will also assume that both variables are jointly quotient. Thus, for the real part and similarly for the imaginary part, its estimator is a mean speech gain vector plus a correction term depending on the noise observation at the secondary channel. As the prior statistics on the speech gain can be computed in advance for a particular mobile device, and the noise observation is known, we just require to estimate the cross-covariance matrix between the speech gain and the noisy observation, and the mean vector and the covariance matrix of a noisy speech at the secondary channel. So to do this, we first adapt our dual-channel speech distortion model to the STFT domain this way. Next, we combine both expressions, so y sub 2 could be fully determined from the noisy observation at the primary channel if we had knowledge about the speech gain term and the noises. And then we assume that the noise variables follow multivariate quotient distributions. And as any linear combination of quotient variables follows another quotient distribution, this expression is linearized by means of a first-order VTS expansion to easily estimate the required parameters. I mean, the mean vector and the covariance matrix of noise speech at the secondary channel. Finally, the cross-covariance matrix between the speech gain and the noisy observation at the secondary channel is similarly derived by following this same scheme. Now I'm going to talk on another contribution, which is dual-channel vector Taylor series feature compensation, which was published at the IIT Signal Processing Journal. Here we extended VTS feature compensation in the Lockmail domain to be performed on the considered dual-channel framework. So first, we assume that the clean speech statistics at the primary channel can be modeled by means of a Gaussian mixture model, and then we define a noisy stacked vector comprising the dual-channel noisy observation. So from these two elements, the Lockmail clean speech features can be estimated at every time frame under a minimum mean square error approach this way, where we can differentiate between two main components, I mean the clean speech partial estimates and the set of posterior probabilities. About the posterior probabilities, by using the Bayes' rule, the posteriors are defined this way, where P of k comes from the clean speech quotient mixture model, and this density function, as we will see, can be approximated by a Gaussian density function. So we just require to estimate the set of mean vectors and the set of covariance matrices. So to do this, we write our dual-channel speech distortion model in the Lockmail domain, and again we assume that all the variables involved follow Gaussian distributions. So I remind that as any linear combination of Gaussian variables follows another Gaussian distribution, we again linearize this dual-channel speech distortion model by means of a first-order VTS expansion to easily estimate the required set of parameters, I mean the set of mean vectors and the set of covariance matrices. In the previous formulation, the secondary channel is being treated in a parallel manner to the primary one. However, as we know, clean speech will be easily masked by noise at the secondary channel, and as a consequence there is a highly uncertain relation between the secondary noisy channel and the clean speech variable. So we've found more robust conditioning the secondary channel to the primary one, thereby decreasing the influence of the clean speech variable. While mathematically this is the same, this leads to a different and more robust formulation, so this posterior is replaced now by this new one, and the required set of statistical parameters are similarly estimated again by following a VTS approach. Finally, we must compute the clean speech partial estimates, and while the clean speech partial expected values are defined this way, it is again necessary to linearize the speech distortion model in order to make inference feasible. So two different approaches are considered here. The first one is based on minimum mean square error estimation and exploits the dual channel information, and the second approach is straightforward and only exploits the information from the primary channel. Considering this second strategy may be more appropriate in our case, since generally the secondary microphone captures a much noisier signal than the primary one. To conclude the presentation of our techniques, now I'm going to talk on our dual channel deep learning contributions that were reported at 2 different papers published at Lecture Notes in Computer Science. Moreover, one of these papers received a Best Paper Award at the conference IBSpeech 2016. In contrast to deep learning, the classical signal processing techniques make assumptions in order to make the problem analytically tractable at the expense of a drop in performance. So here we want to exploit the powerful modeling capabilities of deep neural networks to estimate missing data masks for spectral reconstruction and noise for feature compensation by also taking advantage of the dual channel information. These can be considered as hybrid deep neural network signal processing architectures, which will be extensively and successfully explored in the near future. I remind that in our dual channel configuration, the primary microphone and the secondary microphone observe similar noise power spectral densities, and the speech is more attenuated at the secondary microphone with respect to the primary one. Therefore, we guess that we can easily estimate missing data masks by means of a comparison between the noisy speech power present at the primary and secondary channels. Moreover, unlike other related works using a wide set of features, our DNN directly provides an estimation of the missing data mask by just using dual channel Lockmel features. So we are able to achieve a competitive performance with less computation. And at every time frame t, input features for our DNN consist of the stacked vector comprising the dual channel noise observation. Moreover, the temporal context is also stacked by using a temporal window the size of which is 2 times L plus 1. Thus, if M is the number of filter bank channels, the dimensionality of the input vector is 2 times M times 2 times L plus 1. In regard to the target, this one is an oracle binary mask vector for the corresponding Lockmel feature vector at the primary channel at time frame t. And in this case, the dimensionality of the output is M. And oracle binary masks were obtained by means of a direct comparison between the corresponding clean speech and noisy speech utterances using a 7 decibel signal-to-noise ratio threshold. About the DNN training procedure, the DNN is pre-trained by considering each pair of layers as restricted Boltzmann machines, and then a fine-tuning second stage is performed in which the DNN is trained in a supervised manner by using the backpropagation algorithm considering the cross-entropy criterion. Alternatively, a parallel approach was considered to find a non-linear mapping function between the dual channel observation and the noise Lockmel features at the primary channel. And while the same input features are used, in this case the target vector is the actual noise Lockmel feature vector at the primary channel at time frame t. And again, a pre-training stage is applied, in which it's considered again that each pair of layers are restricted Boltzmann machines, and the mean square error criterion was followed for backpropagation learning. We wanted to explore if our DNN-based noise estimation could be improved by increasing the awareness of the DNN about the noise that contaminates speech, in each case by following a noise-aware training strategy. So to do this, we were inspired by this type of noise estimation, which has demonstrated to be quite accurate. It simply consists of a linear interpolation between the averages of the first and last frames in the logmal domain of an utterance. It's assumed that those frames contain only noise energy. Furthermore, this noise estimation is bounded above by the necessary observation at the primary channel for more consistency. Thus, while the same target vector is used, the input feature vector is augmented by appending a vector containing the average of the first frames and another vector containing the average of the last frames, as well as a time index to indicate the frame's relative position within the utterance. Additionally, we decided to also append the noise sample variance from the first and last frames. Next, I'm going to talk on the experimental evaluation carried out to know the performance of our methods and comparison techniques in terms of recognition accuracy. I mean, in terms of word accuracy and word error rates. About the experimental framework, the databases used were the Aurora 2 to CCTFT corpora and the Time 3 corpus. The Aurora 2 to CCTFT corpora emulates the acquisition of noisy speech by means of a dual microphone smartphone in close talk and far talk conditions, and these databases can be considered as extensions to the well-known Aurora 2 corpus, comprising the recording of utterances of connected digits. And to the set are defined with different kinds of noises in each one: bus, bubble, car, and pedestrian street in test A, and cafe, street, and bus and train stations in test B. The considered SNRs are referred to the primary channel, and they're the same as in Aurora 2. I mean, from -5 decibels up to 20 decibels with a step of 5 decibels. The Time 3 corpus comprises the recording of real and simulated noisy speech by means of a tablet with 6 microphones, 5 of them facing forward and one of them facing backwards, in particular that numbered as 2 in this figure. The Time 3 corpus is based on the speaker-independent medium vocabulary subset of the Wall Street Journal corpus. Male frequency capture coefficients were extracted for speech recognition. And in the case of the Aurora 2 to CCTFT corpora, speech features consist of 13 MFCCs with capsular mean normalization and delta and delta-delta coefficients. Both Gaussian models and deep neural networks were considered for acoustic modeling in the case of Time 3. And when using Gaussian mixture models, speech features consist of 7 frames of 13 MFCCs each, and a linear discriminant analysis, maximum likelihood linear transform, feature space maximum likelihood linear regression, and speaker adaptive training. And in the case of using deep neural networks, speech features consist of 11 frames of 13 MFCCs each. About the backend, hidden Markov models were trained with either clean speech data or multi-style speech data. And only Gaussian mixture models were used for acoustic modeling in the case of the Aurora 2 to CCTFT corpora, as well as one hidden Markov model per digit. As I said, both Gaussian mixture models and deep neural networks were considered for acoustic modeling in Time 3, as well as 2,500 Tryphon hidden Markov model states. For the sake of clarity, generally from now on I'm going to only present results for multi-style acoustic models, as better results are achieved by using these type of models with respect to use clean acoustic models, because of the lower mismatch between the training and test data. So here we can see our power spectrum enhancement results obtained on the Aurora 2 to CCTFT corpora for both close talk and far talk conditions, and in particular represent word accuracy as a function of the signal to noise ratio. And in these captions, next to the name of every technique, we can see the average word accuracy from -5 decibels up to 20 decibels. First, baseline means using noisy speech features with no compensation. And as we can see, the best results are achieved by our dual channel spectral weighting with bias correction and noise equalization. Both delay and sum and NVIDIA beamforming worsened baseline performance, and this was expected because we have only two microphones very close to each other, one of them placed in acoustic shadow with respect to the speaker. In contrast to NVIDIA beamforming, our technique PMVDR improves the baseline performance. So we confirm that this card in the face as used by NVIDIA beamforming is positive, especially in closed talk conditions. Finally, we can see that dual channel spectral subtraction and PMVDR provide similar results. We can express these techniques in terms of dual channel linear combination, and it is easy to show that the corresponding weights tend to be the same as the speech gain term is up to 1 goes to 0, something happening in our case as speech is much attenuated at the secondary microphone with respect to the primary one. Nevertheless, we should not forget that both techniques are different, and in the thesis report it's demonstrated that PMVDR has nicer properties than DCSS, as for example PMVDR is a more robust method. Here we compare our minimum mean square error relative speech gain estimator with a technique to compute this term based on eigenvalue decomposition of the clean speech spatial covariance matrix derived from complex Gaussian mixture model based time frequency masks. Moreover, this eigenvalue decomposition based method was recently proposed by the winners of the Chain 3 challenge. The speech component at the secondary channel can be safely neglected in close talk, but not in far talk conditions. This is confirmed by our results, as correcting bias with our technique barely affects in close talk conditions, in contrast to far talk conditions. On the other hand, the eigenvalue decomposition-based method introduces a harmful mismatch, as it worsens the biased dual channel spectral weighting. Our power spectrum enhancement proposals were also evaluated on the Chain 3 corpus in terms of word error rate. In this case, a virtual primary channel is obtained by means of NVIDIA beamforming, using the 6 microphones of the tablet to be used as primary channel. Additional techniques are considered for comparison: a soft mask weighting in the local domain, a Wiener filtering with the same post-processing as that used by our dual channel spectral weighting, as well as 2 beamforming post-filters. As expected, similar trends are achieved by employing Gaussian mixture models and deep neural networks for acoustic modeling. Again, the best results were obtained by our dual channel spectral weighting technique with bias correction and noise equalization. Furthermore, 5 channels means that the 5 front sensors in the tablet are being considered, while 6 channels indicates that also the secondary sensor is being employed along all the front microphones. Thus, while considering the secondary microphone slightly improves NVIDIA beamforming, similarly to what happened in the case of the Aurora 22 CCTFT Corpora, considering the secondary sensor for delay and sum yields a drop in performance. Although the secondary channel has already been used to define the virtual primary one, these results reveal the convenience of treating the secondary signal in a differentiated manner, since it can be further exploited to provide useful information about the acoustic environment. Thus, considering DNN-based acoustic models, the percentage change between NVIDIA 5 channels and NVIDIA 6 channels is only 0.36%, while the percentage change between NVIDIA 6 channels and our dual channel spectral weighting with bias correction and noise equalization is greater, 2.35%. We compare again our minimum mean square error based relative speech gain estimation method with the eigenvalue decomposition based technique previously presented. What draws attention is that correcting bias with our method worsens worsens a biased dual-channel spectral weighting and a deep neural network acoustic modeling. This can be explained because NVIDIA beamforming yields a stronger homogenization of the noise at the virtual primary and secondary channels, so the substantial improvement only comes when bias correction and noise equalization are applied together. Moreover, we can see that both speech gain estimation methods provide very similar results. At this respect, we should take into account that the relative speech gain prior statistics used by our method are derived from estimated multi-channel clean speech by using the closed-talk microphone data from Chime 3. Nevertheless, according to the measured time complexity, our minimum mean square error based approach is much more efficient, as the eigenvalue composition based technique involves an expectation maximization iterative procedure. In this slide, we can see our vector Taylor series feature compensation, where the accuracy results obtained for the Aurora 22 CCTFT corpora. As we could imagine, the simpler approach for clean speech partial estimate computation with subscript B and only using the information from the primary channel provides better results, as the secondary microphone captures a much noisier signal than the primary one. Moreover, the dual channel approach is clearly superior to the single channel approach, as it exploits spatial properties of the clean speech and noise signals by means of a speech gain vector and the spatial covariance matrix of noise, respectively. We also confirmed that the alternative posterior computation based on conditioning the secondary channel to the noise observation from the primary one gives better results than the original posterior computation based on this tagged formulation. Finally, while VTS compensation has the ability of reducing the noise mismatch, it's much more able to precisely estimate the actual clean speech features, which can be appreciated under clean acoustic modeling. In the case of Chime 3, VTS feature compensation exhibits a poor performance, as it even degrades NVIDIA beamforming, again applied to generate a virtual primary channel. At this respect, poor performance of VTS feature compensation under multi-cell acoustic modeling has already been reported in the literature. Unfortunately, a more precise explanation to this fact is not given. While VTS feature compensation still improves NVIDIA beamforming under clean acoustic modeling, this word error rate result is still too high in comparison with a simple multi-condition scheme. This way, no more VTS results have been reported here, as this is the general trend for this task. So our dual-channel spectral weighting with bias correction and noise equalization used as NVIDIA post filter provides our best result for Chime 3. Let's return to the Aurora 22 CCTFT corpora, and as we can see from our results, the higher the signal-to-noise ratio of the speech data, the higher the recognition accuracy provided by VTS feature compensation. Therefore, dual-channel power spectrum enhancement can be used as pre-processing to leverage VTS feature compensation. There are substantial improvements, accuracy improvements, when using both PMVDR and our dual-channel spectral weighting along with single-channel VTS feature compensation with respect to only use single-channel VTS feature compensation. Such improvements are reduced in the context of dual-channel VTS feature compensation. This makes sense, as the same spatial properties of the clean speech and noise signals are being exploited by both our dual-channel power spectrum enhancement methods and dual-channel VTS feature compensation. We can highlight that these combination results are the best results obtained by us on the Aurora 22 CCTFT databases. As our dual-channel deep learning methods specifically exploit the power level differences between the two channels of the device, only results for closed-talk conditions on the Aurora 22 CCT database will be presented from now on. In this slide, we can see the experimental results derived from using missing data masks for spectral reconstruction. So, the spectral reconstruction technique TGI is combined with missing data masks calculated by using our DNN-based approach, also with Oracle masks, and finally with masks obtained by thresholding the a priori signal-to-noise ratio of the primary channel, estimated by means of a maximum likelihood approach, TSNR. Training input data consisted of a mixture of samples contaminated with the noises of tested A. Thus, if we take a look at the results for tested B, we can observe that the DNN exhibits some generalization ability to unseen noises during the training phase. Moreover, because the performance tends to saturate for L equals 2, I mean the size of the temporal context, and greater values, one guesses that the DNN is mainly exploiting the power level difference between the primary and secondary channels. Since most of the information required to provide a power level difference based estimate at frame t is close to that frame, the proposed DNN approach does not benefit of further increasing the length of the analysis window. While the use of Oracle masks is an upper reference, it is clear that our DNN approach provides more accurate masks than the SNR-based technique for comparison. As was the case of VTS compensation on time 3, we can see here that the performance of those methods that try to precisely estimate the clean speech features, like the spectral reconstruction technique TGI, can be severely limited when using multi-style acoustic models. Similarly, in this slide, I present the DNN noise estimation for feature compensation results. Apart from DNN sub 2, which is our dual-channel approach without noise-aware training, as presented, we evaluated what we've called DNN sub 1, which similarly estimates noise, but only using the primary channel as input instead of the dual channel. The superscript NAT indicates that either DNN sub 2 or DNN sub 1 integrates noise-aware training as also presented. All of them are combined with VTS feature compensation. And we can highlight the following about the results. For both types of acoustic models, the best results are achieved by DNN sub 2, which is clearly superior to DNN sub 1 as it exploits the noise reference from the secondary channel. According to the results for tested B, DNN sub 2 exhibits some generalization capabilities to noise conditions not seen during training. Finally, it's interesting to see that NAT improves DNN sub 1 but degrades the performance of DNN sub 2. This could be explained because the secondary channel is a better noise reference itself than the information considered in our NAT-based approach, which introduces a greater uncertainty. To conclude our experimental analysis, we compare DNN sub 2, which has exhibited the best performance, with different single-channel noise estimation methods from the state-of-the-art, as well as with a dual-channel method specific for dual microphone smartphones employed in closed-talk precision, PLDNE. Of course, all of them are used in combination with VTS feature compensation. More in particular, PLDNE assumes both a homogeneous noise field and that clean speech at secondary channel is much attenuated with respect to the primary one. As can be observed, on average, and for all the SNRs considered, DNN sub 2 shows the best performance. It's interesting to see that linear interpolation is at the same time quite simple and very competitive. To conclude this presentation, now I'm going to summarize our conclusions and possible future work. So we confirm that the multi-channel information coming from mobile devices with several sensors can be exploited for noise-robust speech recognition purposes, and at this respect, we've developed a series of contributions intended to operate in a dual microphone setup, where the performance of classical beamforming is poor, as we only have two microphones very close to each other, and one of them placed in an acoustic shadow with respect to the target signal. So designing specific solutions is mandatory to achieve high recognition accuracy on dual microphone mobile devices. And for experimental purposes in this context, we developed the URA2 to CCTFT corpora, which can be considered as contributions of this thesis. And the best power spectrum enhancement results were achieved by our dual channel spectral weighting with bias correction and noise equalization, with our minimum mean square error based speech gain estimation method, which provides similar or better results than an agent value decomposition based method with a fraction of the computational complexity. We also confirmed that discarding the phase information is beneficial to overcome the limitations of classical MVDR beamforming when applied to the considered dual microphone framework. And as expected, we showed the better performance of the dual-channel VTS feature compensation approach with respect to the single-channel one on the Uratu to CCTFT databases. And for dual-channel VTS feature compensation, it was proven to be more robust, modeling the conditional dependence of the noisy secondary channel given the primary one than following the original stacked formulation for posterior computation. And next, we were able to estimate accurate missing data masks and noise by exploiting the powerful modeling capabilities of deep neural networks and also by taking advantage of the dual channel noise information. And in this context, the use of the secondary sensor itself can be understood as a more robust kind of noise-aware training strategy. And finally, we conclude that our contributions broadly showed an outstanding performance at low signal-to-noise ratios, which makes them promising techniques to be used in highly noisy environments, such as those where mobile devices might be used. As possible future work, we would like to extend our different proposals to operate on different mobile devices with other small microphone array configurations. I remind that the best results for VTS feature compensation were achieved when using our simpler approach for clean speech partial estimate computation, only using the information from the primary channel. So we would like to take advantage of a multi-channel noisy observation also for clean speech partial estimation. And with respect to our DNM-based proposals, we would like to perform an extensive search regarding the architecture and training configuration. So for example, we would like to use recurrent neural networks to better exploit the temporal correlations of the speech signals, and we would like to investigate the use of additional or different kinds of features. So for example, pitch-based features are able to improve the generalization capabilities of deep neural networks in this context. And finally, we would like to extend our DNM-based proposals to deal with a hands-free or far talk scenario. And with this, I've concluded my presentation. Thank you very much for your attention.